Hello everyone, the paper I share with you is vulnerability detection based on wide graph and deep learning. Today's sharing is introduced from following three parts. The first part introduces the background knowledge, some existing challenges and the mainstream code similarity detection, and finally, the main contribution of this paper. The second part introduces the basic design steps, mainly include 5 stages: data collection, static analysis, vector input, white feature graph conversion, and graphic compression. The third part introduces the evaluation method. Okay, let's introduce the first part to introduce the background knowledge. The rapid development of computer technology has prompted the development of the economy and society. However, with the increasing number of computer programs, software vulnerabilities are also increasing. According to common vulnerabilities and exposures report, the number of software vulnerabilities has been increasing rapidly in recent years. The popularity of open source software makes it easier for software vulnerabilities to spread among computer systems. Once used by attackers, it may cause huge losses. Manual vulnerability detection and verification requires a lot of human resources. Researchers need to deeply analyze and understand the target program, and experience and knowledge are difficult to review. Therefore, the automatic detection and verification of vulnerabilities has always been a research hotspot. The primary problem of vulnerability detection is the uneven quality of vulnerabilities. In addition, an excellent deep learning algorithm may need to train millions of samples to get a good model, but in reality, it is difficult for the same type of figure samples to reach such a scale. Another problem is that the graph-based structure can easily lose the source information, and at the same time it can easily increase unnecessary compression overhead and introduce a lot of unless information. What's more, deep learning has been successful in many fields, and it is also applicable to static analysis of programs. Although there have been many examples of deep learning models applied to vulnerability detection, there are still some limitations, such as CNN and RNN, which can't handle the non-sequential information in the source code, but can only capture the surface structure. Code similarity detection plays a very good role in vulnerability detection. Its common steps are generally divided into 3 steps. The first step divides the test program into smaller compression units, which can be of any granularity level, such as files, classes, functions, basic blockers, or statements. The second step is to convert the compression unit into a representation form, which can be a graph, a tree, or some other structure. This can effectively represent the original code and facilitate compression. The third step is to impose the converted unit into a compression algorithm. We compare the converted unit with the always fragile unit and output the code with high similarity. Based on the method of code similarity detection, we propose a vulnerability meaning model, and our contributions mainly include three aspects. Firstly, according to the vulnerability triggering logic and programming style, a code variation method is designed. It generated a large number of relatively valuable vulnerability that match graph models. Secondly, the model pays more attention to the features of a vulnerability function. Thirdly, the vectorization method of code block in this model can keep rich syntax and semantic information of functions and simplify complex graphic information. Next, let's go to the second part and introduce the basic design of the model. Figure in the main framework of our model, including data collection, static analysis, vector input, wide future graph conversion, and graph compression. In the data collection stage, our model consists of two models, a data collector and a variant code generator. According to CV site information, the data collector will directly obtain the involved function name, file name, affected program version, and patch, and identify the function location with the help of patch. The variant code generator will obtain the ranking of sensitive keywords by text rank and TF-IDF algorithm, and divide the code into vulnerability related and vulnerability not related statements by keywords. Then, by defining variant rulers, it will generate a series of vulnerability codes that meet the vulnerability triggering logic and programming style of general programmers. Static analysis is the key model of our model. It uses scan build to analyze the program, converts each into a function control flow graph, and stores the AITS information of each node's corresponding code block. When too much information is added to the chart, the information will be too complicated, resulting in difficulty in the vector input part. We tie the text RN, GRU, BERT, and other deep learning models, and converted the syntax and semantic information of local code blockers into vectors, which were input into the white graph. We save the syntax and semantic information of code blockers as much as possible through hidden layer vectors. From the perspective of vulnerability, the contribution of code to vulnerability is different. We define two wide distribution principles: the allocation rulers of row weight and node weight, as shown in the figure, and are the codes and graphs that we have allocated rights to. Finally, we all know that graph similarity is an NP problem, and it is not easy to find the optimal solution. Therefore, we calculate the similarity between two right-future graphs by graph matching. We define an algorithm that can output the similarity between two right-future graphs. Finally, in order to verify the effectiveness of the method and fully demonstrate the functions of our model, we compare our model with 4 state-of-the-art models, including code similarity methods based on text, sequence, tree, and graph. We see that the performance of each method is shown in the first figure. Compared with other methods or models, our model has obvious advantages in all aspects. We can see the second figure, which shows the performance of our method under different efforts. To prove the efficiency of our method in the field of vulnerability detection, we summarized the time overhead of 2 data sets, as shown in the figure. We mainly spend time in 3 aspects: static analysis, right-future graph conversion, and WFG compression. The cost is mainly focused on static analysis, because that step needs to use scan build to pass the whole program. The cost of right-future graph transformation is relatively small, and its main cause are vector transformation and weight distribution. The first 2 steps only need to be operated once. The graph compression speed is very fast. It takes only 72 seconds to complete the compression of 1528 right-future graphs with vulnerability WFG, which undoubtedly proves the potential of our method in processing large amounts of data. Of course, our methods also have some deficiencies. First, the data processing method in this paper can only deal with vulnerability code at the functional level. If the vulnerability spans multiple functions, or even multiple files, the data processing method in this paper is powerless. Secondly, the model aims to solve the binary classification problem and can't solve the problem of multiple vulnerabilities. Third, the detector can only detect 3 vulnerabilities. We will try to migrate to other languages to meet more vulnerability detection requirements. The above is the paper sharing. Thank you again for listening.